All right. Now there's another kind of type of problem. It's kind of a work quadratic kind of problems where you have like people doing a certain amount of work by themselves and together, and you get some amounts that get done in a certain amount of time, and you're trying to figure out how much they might do individually or something like that. I'm going to do essentially the same problem, but from the perspective of filling up a water tank with pipes of water. But you can think of if you ever come across these kind of work problems, I would suggest just thinking about it in terms of filling up a water tank with two pipes coming in or whatever, because it's much more concrete. All right, so we have a tank, water tank, and two inlets, one large and one small. Now they typically fill up together, and it takes fill up together. So basically you've got this tank and you've got large and small. So large is filling up the tank a lot, and the small is filling up a little. And I should probably there you go. So they're just tumbling in. Okay, so they fill up together, and they takes 3 hours to fill up the whole tank. Big tank, fills up together. Now we also know that the larger one by itself fills up quicker by 2 hours than the smaller one. And so what are the times to fill up? So that's the basic question. So it's kind of, again, one of these, like, really, why would you just, how would you know that the larger one fills up quicker by 2 hours than the smaller one without actually knowing how quickly they filled up, right? I mean, I guess maybe there's some kind of size thing you might know, but I mean, I feel like if you, whatever information you knew that could compute that, you could probably figure out the thing you wanted from that information directly. So again, these problems are a little sometimes fake. But what's the idea here? The idea here is that the volume, so we've got the large, well, there's only one volume, but the volume to fill up is equal to the flow rate, so you have the large one, times the time of the large one. And the volume of the small one, I mean, there's only one volume, same volume. That gets filled up, flow rate times the time, S, right? And so, and then the volume, if you add them, the flow rates, times the time of both, which was 3. And we also know that the time of the larger one is the time of the smaller one minus 2 hours. Okay, that's the information we're given. Now, this is the part you really need to focus on, is being able to write down this information. So where did all this come from? Well, I've got a rate of fill in the tank. And what does that mean? That means volume per time. That's the idea. We're assuming it's a constant rate. These are assumptions. And that, so as the water goes in, it accumulates over this time. There's a certain time to fill up the tank. And that's really defining the flow rate. So this is really defining the flow rate as the time. So you would observe the tank being filled up over this time, and then you would divide the volume by that time, and that would give you your flow rate. That's the basic notion of the flow rate. Now, so those are the two things separately, and then when I put both of them on, I'm combining their flow rate, right? For whatever amount of time they're both on, I multiply each flow rate by that time, I get a volume, and that's the volume of that thing. And we're saying that if I do combine them like that, it takes 3 hours to fill up the tanks. So that's that. Now, the time for filling up the larger one, the larger one fills it up quicker. So it's a smaller time, and that's smaller time is given as being less than 2 hours. So this is the thing. I've named a lot of stuff. I've defined a lot of relationships here. I don't know how to solve this yet. I don't know. My brain is like, I don't know. I'm just focusing on, what do I know? How do I get it into some symbols, some math, right? Like, I'm not thinking about the solution yet. I'm just thinking about, I don't really know what's going on. And so, what am I even going to go for here, right? Well, let me try to simplify some of this stuff. So, as I said, the flow rate here, you don't really need the flow rates. They're not really asking for that. And you'd have a hard time really getting a number for that because you don't know the total volume of the tank. It would have to be in terms of the volume of the tank, be V over something. So we're just going to get rid of that whole thing. So this V here is put in the definition of this flow rate of V over TL. And then the same thing for the flow rate of the small one. And of course we have this 3 here. Now notice that V appears in all of the terms. So I can just divide by V. And now I don't, that's why I don't need this information. So I've got 1 equals 3 times 1 over TL plus 1 over TS. Okay, good. Now, if that's all I had, I wouldn't be able to solve this problem. But I know something. I know that TL is TS minus 2, or that TS is TL plus 2. I like pluses. I'm a positive kind of fellow. So 1 over TL plus 1 over TL plus 2. Now, if you did have a question where they were asking you for a particular time of the large one filling in, or the time of the small one filling in, that's the variable you should go with, so that when you get your answer, it's the answer. But I didn't say which time. I want both times, so it doesn't matter. Pick one. I like this one. And now, of course, we could just, because now there's only one variable, I can just call that 1 over x, and 1 over x plus 2. Okay? Good. Nice. So this is, how we want to proceed, basically. And now, so let's try some times, right? So, and I guess I could have done this before, but let's say it takes I don't know. So 3 hours was the combined rate. So together, you know, the times are going to be, I mean, separately, the times are going to be longer. There's a 2-hour difference kind of in here somehow. So the smallest one would you know, I don't know. Let's just try 5. It seemed reasonable to me. So the time of the small one is 7. Remember, the small one takes longer. So it's 5 and 7. And so now we have this thing. 1 equals 3 1/5 plus 1/7. And you know, this is, let's say, like 0.2 and 0.14, 0.34 times 3, 1.02. So that's kind of actually close. So I'd probably just go like, yeah, it's about 5 and 7. Guess and check to the win. However, how would we do this out algebraically? Well, the common denominator here is x times x plus 2. So we just multiply everything through by that. And we have 3 times, we have x plus 2 plus x. Alrighty. And so x times x plus 2 equals 3 times 2x plus 2. Alrighty. X squared plus 2x equals 6x plus 6. Subtract here, x squared minus 6x from that is minus 4x equals 6. And now, what do we have here? Well, x squared minus 4x is equal to x times x minus 4. So this is 0 and 4, so 2. Nice. And so what do we have? We have x minus 2 squared. And then the 2 and the 2 is minus 4 as well. Okay, so we have x minus 2 squared minus 4 equals 6. X minus 2 squared equals 10. Square root of that. X equals 2. Again, I'm going to want to add the plus there. 2 plus the square root of 10. Cool. And let's see, if I want to use the quadratic formula, that would be minus b, so that's a 4, plus or minus the square root of 16 minus 4ac. So that sounds like 24 over 2. So 2 plus or minus, this was 40, which is equal to 4 times 10. So I can pull out the 4, it becomes 2, square root of 10. Oh, sorry, I'll just do that slowly. And then 2 plus or minus the square root of 10. I cross out the minus because 2 minus the square root of 10 is negative, as square root of 10 is slightly above 3. And there we go, 2 plus the square root of 10. So there you have it. Graphically, of course, we could come over here to GeoGebra. Now, I can actually graph after I plugged in x for these things. Did I get my parentheses right? So there's that, and I want that to be equal to 1. And I can just take the intersection here, and there we go. And then there's also another one over here there, but that's negative, so that's silly. So we don't need to do that. I can then also graph, say the parabola that I had. Let's say x squared minus 4x. And I think that was supposed to be y equals 6 for that one. So that's when I was completing the square part. I had it on different parts. I look at that. There we go. That didn't work out terribly. Oh wait, sorry, 5.16, yeah. That's good. That's right. And then I could also graph same thing, but with the -6. So this is kind of the form for the quadratic formula. And here I'm going to intersect that with the x-axis, and I get the same coordinate. So visually, those are all three kind of different ways of graphing to get the same solution, right? So these are different functions that I'm graphing. They're crossing in different ways with things and whatever, but they all have the same x-coordinate for the solution. All right, and that's a kind of a nice tip in terms of trying to figure out where your algebra might have been different. So if you graph something earlier on in your work, and then you graph something later on, and they're giving you different solutions, then you know something went wrong somewhere in between. All right, so that's filling up a water tank. You can also say it in the following fashion. So kind of a work. You could say 2 workers complete a job together in 3 hours. Separately, A completes jobs quicker than B by 2 hours. B by 2 hours. So one reason I don't really like these problems is, of course, that they're making this assumption that when you add workers together, their productivity goes up by simply combining what they had done before. So if it takes one person 6 hours to get through a bit of work, so that's 1/6 of the work per hour, and then somebody else gets through the work in 4 hours, the assumption is that, so a quarter of the work per hour, if you have them both working on the same thing, it's 1/6 plus 1/4 in terms of what they get through in the hour. So they're additive in just the same amounts. This doesn't strike me as very realistic. I find that when I work with other people, there are times when our productivity goes way up because we're bringing things together that the others didn't, and so our productivity actually improves, or we're able to divide up tasks in such a way that we can really get fast at whatever we're doing, right? Other times it gets way slower because, you know what? Just talking. So this is one of these examples of where, ooh, that sounds nice, and it's a good first stab at a problem, to say like, well, that person took 6 hours to do that, and that person took 4 hours, and if we put them together, they're going to do it in much less time, right? That's a good starting point. I think it's generally wrong, but anyway, so I would prefer the water kind of problem because it actually makes sense that when you put the 2 pipes together filling up a tank, that their individual rates are still staying the same, and it's filling up, and therefore get it. But it's the same exact setup. You know, you can just kind of like just replace the V's with W's, and I don't know, maybe still F for flow rate of in the flow while working at times, but you know, like it would all be the same. And that's also important to realize commonalities between different kind of possible scenarios, and be like, oh, that's the same. It's the same thing. It's just some different language, some different words. As I said, they're not exactly the same because I think the water pipe actually makes some sense in terms of the assumptions of a constant rate, and the people doesn't. But, and also, like, you know, I don't know. But I guess if you had people separately like that, that would be different. Okay, so that's enough of those problems.